Good time of the day, everyone. Welcome to VSAONLINE. It is my pleasure to host today Luke Yi and Sarah Ashur from Stanford University. And without any further delay, I leave the floor to you, Luke. So you introduce the title and go on with your presentation.
Sure. Thanks for the introduction and thanks for having me. My name is Luke, and I'm going to present hardware-aware static optimizations of hyperdimensional computations. This is a joint work done by me and my advisor, Sarah Ashur. We are from Stanford University, and this work has been accepted by the Programming Language Conference, UPSLA 2023. Okay, so before I talk about our system, let me first briefly introduce emerging hardware technologies. So emerging hardware technologies offer many benefits, such as higher information density. For example, the resistive RAM memory device can store more than 1 bit in one cell. And also some offers non-volatility. So the power is off, the information is still there. And also some emerging hardware technologies offer ultra low power. However, currently there's some issues with these emerging hardware technologies. Sometimes they occasionally corrupt bits, which means they have higher bit error rate. And as pointed out by prior work, hyperdimensional computation can be a suitable computing paradigm for emerging hardware technologies because it is naturally error resilient, highly parallelizable, and easily implementable in the hardware. And in this work, we also show that HTC is also analyzable for emerging hardware technologies. And in contrary, it's very hard to reason about hardware errors in classical computations. So we're interested in developing software tools for efficiently implementing HTC on emerging hardware technologies. Okay, now let me make an outline of this talk. The topic of this talk is our system HIME, which is a static analyzer for HTC programs that automatically finds the optimal hypervector sizes and distance thresholds. To give you some context, static analysis is to analyze the program without executing it. And our system HIME can directly analyze the effect of hardware error, which are useful for emerging hardware technologies that are error-prone. And in the system of HIME, we combine some theoretical results from the VSA community and also introduce some extensions to build workable devices to applications analysis. We target binary scatter code or BSC HTC in this work, but our approach can be generalized to work with other HTC variants. Because we assume the audience has a similar background and is familiar with the HTC basics, we will introduce the terminology and the problem statement briefly by example. Okay, our example is a knowledge graph, and we want to encode this knowledge graph in HTC. So this is a knowledge graph example. So this is a student knowledge graph with 5 nodes or concepts. The concepts are banana, apple, Jack, Mary, and tennis. And the ages is from one node to another, and the label on the age is called the relation, and the directionality of the age is called the interaction. And we're interested in such a query. In this knowledge graph, how many students like apples? Well, the expected answer is 2, because there are 2 nodes that have an outgoing age to apple, which are labeled likes. Okay, so now let's show how we can encode this knowledge graph and also the query in the HTC. So first, let's encode the ages. Well, we encode each age as a binding of the direction, the relation, and the concept. So for example, this age circled in red is represented as act, binds, likes, binds a banana, because for Jack, this is an outgoing age. So here, this is act, and it's labeled likes, and its target is banana. And for banana, this age is encoded as target binds likes binds Jack, because banana is the target of this age, and this age is labeled likes, and it's from Jack. And we will do the bottom up. So now we have the encodings for the ages. We will then construct the hypervector encoding for each nodes. For example, for Jack, we would then encode its hypervector as the bundle of all the incident edges to this node. So Jack's representation is then the bundle of these 4 edges. Okay, with the hypervector for each node, we then store all the node hypervectors, or the hypervector data structures, we call them, to the item memory. Each row in the item memory is a mapping from the concept label to the hypervector that encodes the list of edges incident to this node. Now that we have the data structure, how do we encode the query and execute the query? So the query encoding is the same encoding procedure as the knowledge graph edges, because essentially we are querying the membership of an edge. So the apples query is encoded as act binds likes binds apple. Now, what we would do is that we would calculate the query hypervector, the distances from the query hypervector to each row in the item memory. And based on their distances, we determine whether there is a match or not. Now that we have the distances, which knowledge graph nodes should we return? Well, conceptually, we would return the hypervectors with a small distance, because a small distance indicates the correlation between these 2 hypervectors, which may implicate that the hypervector that encode edge set may contain this edge we are looking for. However, currently we have incomplete information. For example, what distance threshold exactly should we use? How should we distinguish between a small and large distance? And also, how big are these hypervectors exactly? Further, how do we take into account the hardware errors in the target hardware platform? Okay, so what are the current practice for setting the hypervector size and distance thresholds today? Well, there are 2 approaches. The first approach is called static assignment, where you conservatively set the hypervector sizes to a high dimension, such as 10,000. And the second approach is dynamic tuning, where you tune the hypervector size and also some other parameters on a set of test data structures and queries and random codebooks. However, these 2 approaches have obvious cons, and we will show the cons in the example. Well, we try to implement the dynamic tuning on the apples query we're interested in, and we configure it to try to deliver a 99% accuracy. So with dynamic tuning, we tune the parameters on the apples query on this exact knowledge graph with the random codebooks. And this produces parameterization with n equals 117 bits and the threshold, and the total optimization uses 34 seconds. Well, as expected, this parameterization indeed achieves 99% accuracy on the apples query on this knowledge graph. However, we're interested in whether this parameterization can generalize well to other similar knowledge graphs with the same node cardinality. But we find that on random knowledge graphs with also 5 node and same node cardinality, the accuracy this parameterization achieves is only from 97.6% to 99%. And this means the parameterization did not generalize well to other random data structures. And it should be noted that the fluctuations are only on very small data structures. If the data structure is even more complex, the fluctuations can be even higher. Of course, we can try to optimize further this approach by individually tuning the thresholds for each node cardinality in finer granularity. But this will further increase the time required to tune the parameters, because more parameters means larger parameter space. Well, what about static assignment? If you conservatively set the hypervector size to 10,000, there is still one problem. You don't know which threshold you should use. So in this approach, you still need to dynamically tune a threshold on random hypervectors and random knowledge graphs and queries. With such a high dimensionality, you would get nearly 100% accuracy because the information resolution is very high. However, you are using nearly 100 times the required size that you can achieve 99% accuracy. So to sum up, the cons of these approaches, for static assignment, it is resource inefficient and it cannot be used to set the thresholds. And for dynamic tuning, this approach lacks accuracy guarantees, and the parameterization generated by dynamic tuning may not generalize well across other queries and data structures. And also, this is very computationally intensive as the search space would grow as the number of parameters grow. Okay, now let me present sound parameter optimization with HIME, which can address these issues. Unlike static assignment or dynamically tuning that works with Monte Carlo simulations on random hypervectors or random codebooks, HIME analytically derives the hypervector size and the set of distance thresholds for HDC-based data structure. Also, HIME provides accuracy guarantees over all the queries and data structures that are covered by a user-provided HIME specification. So what is a HIME specification? So let me now show the HIME specification for the example knowledge graph that we have seen. So as a reminder, the maximum node cardinality or the degree of the graph is 4. So let's look at the second line here. The apps data here specifies that the data structure expression is a bundle of at most 4 hypervectors together, where each hypervector is in the form of a product of interaction, relation, and concept. This is equivalent to say that each node has a maximum 4 edges. And the first line, apps data query, specifies the HD expression for the query, which is also an edge. And the third line here specifies the threshold query we're interested in. The first 2 parameters are the HD expressions for the query and data structure. The third parameter is called K, which specifies the intersection size of the query and data structure that we are interested in. We will elaborate on this further in the later slides. And the fourth parameter is the minimum or desired accuracy we want to achieve. And optionally, the user can also specify the desired false positive and false negative rates in the last 2 parameters. And based on this specification, HIME chooses the hypervector size and the distance thresholds that satisfy all the query constraints. And the parameterization generalized by HIME can hold for all the data structures and queries that satisfy this data structure and query specifications. So we run HIME on this specification on this knowledge graph apples query, and HIME produces a parameterization with n equals 173 bits, which is slightly higher than dynamically tuning, and also a set of distance thresholds. And the accuracy HIME achieves on random data structures range from 98.9 to 100% accuracy. This is close to or even higher than the specified accuracy. And the runtime of HIME is only 14 milliseconds, which is hundreds times faster than the dynamic tuning. Okay, we just seen an example of a threshold-based queries, but HIME can also work with another type of query called winner-take-all queries. Here we will also present a winner-take-all query as an example. The example here is a database analogy query. So in this database, each record represents a country, and each data record has the attributes of the countries, such as names and the currencies. And the query we're interested in is called an analogy query in the form of such as what is the dollar of Mexico, or what is the equivalence of dollar in the Mexico country. So the expected answer should be peso, because dollar is the currency in USA and peso is the currency in Mexico. Well, we'll first show the HD encodings of this analogy query. So for each record is represented by a bundle of the key-value bindings. And the query is constructed as the binding of 2 data records and the value we're interested in. Well, this will produce an approximate representation of the hypervector concept we're interested in. So the query execution is to calculate the distance from the query hypervector to all the concept hypervectors, and we find the best match and return it. Well, here we show the HIME's accuracy specification for this analogy query. Similarly, the first 2 app's data statements specifies the data structure and the query HD expressions. So here, the 100 tells us that we assume the maximum number of attributes for each data record is 100. And the last line, winner-take-all query, specifies the analogy query we are interested in. And similarly, the first two parameters are the query and the data structure expressions. And the third parameter is the intersection size K. And the last 5 parameters are the two accuracy constraints, which we'll elaborate later. Okay, so currently we show how HIME can support winner-take-all based and threshold-based queries. But how does HIME actually incorporate the hardware error into our analysis? Well, HIME works with a hardware error specification that describes the per-bit error rates for different compute and memory elements. This is an example of a hardware model. Actually, this is an example that specifies the 2-bit per cell RRAM. And the first 2 lines specify the bit error rates for any bit error rate happens in the memory technologies and the approximate content addressable memories we used for the item memory. And the last 2 lines specify the bit error rate that happens in the binding or bundling logic. HIME's HDC expression together with this hardware model specification capture a class of computations on a class of hardware technologies. Okay, that's an overview of HIME. And how does HIME work exactly? Now, let's dive into the details. Well, HIME's system structure is like this. It has 2 inputs, and it generates parameterization of the HDC. The first input is the HDC specification. And here is the language grammar for the HDC specification. We don't need to read this language grammar in detail, but the point is that HIME can support nested product of sum and sum of product HD expressions, and also threshold-based and winner-take-all-based queries. And the second component, or the second input, is the hardware model. And similarly, this is the grammar, and HIME can support specifying the bit error rates in the memory locations and also in the HD operators. And based on these 2 inputs, HIME would optimize and produces the optimal hypervector sizes and optimal distance thresholds. Okay, so now let's break down HIME's internal mechanism and take a closer look. HIME can be broken down into 3 major components. And on the top level is the optimization algorithm. And there are 2 other components called analytical model and accuracy analysis. On a high level, the optimization algorithm searches the hypervector size n and provides it to the other 2 components. The accuracy model then uses the hypervector size and the other 2 inputs to derive the distance distributions, which the accuracy analysis use to derive the optimal thresholds and the expected accuracy. And now there are 2 cases. If the accuracy analysis finds that the accuracy constraints cannot be satisfied with the current hypervector size, then it will inform the optimization algorithm that the hypervector size n could be larger, or should be larger, and otherwise it will inform the optimization algorithm that the size n could be smaller. Well, before I talk about any formulations in our HIME system, I'll first give a summary of the theoretical formulations used in HIME. So for the winner-take-all case, where the number of winner is 1, and also for 2 cases of the expected distances, the formulas are derived by the prior work, and we extend to include the general winner-take-all cases, and we support soft constraint analysis, and also add another case for the expected distances, and we incorporate the hardware errors. Okay, as you can see, at the core of HIME's system is the accuracy analysis procedure. So let's talk about the accuracy analysis procedure first. Well, now let's introduce in detail what the intersection size and the distance thresholds mean. in the specification. So we formulate each HT query as testing if the intersection of the query and the data structure hypervectors has a size of at least k. If it has a size of at least k, then we call them a match. Otherwise, we call them a not match. For example, if we want to do a single element membership test, then we should set k to be 1. And if we want to test whether a set k is contained or is a subset of the other set S, then we would set k equals the size of T. And depending on whether the data structure and the query match or not, the distance between the query and data structure hypervectors follow certain distributions. And we call the distribution where they match a match distribution, or phi m. And we call the distribution where they don't match a not match distribution, and also phi nm. And these two distributions are computed from the query and hardware specifications and is derived by the other component of HIME, the analytical model, which we will talk about more later. Now let's just assume that we already have these two distributions. Okay, I'll first give some intuitions of HIME's accuracy analysis procedure for the threshold-based queries. So this is the threshold-based queries for the knowledge graph and apples query, which we've just seen in the example. So in this case, k equals 1 because we are doing a single element query. We're querying whether an edge belongs to each of the edge site. And these are the two distributions we talk about. The blue one is the match distribution, and the red one is the not match distributions. And let's say now in the item memory, we have 10 hypervectors. Essentially, we have 10 nodes, and let's say that 5 of them are matches for the query, and the other 5 of them do not match the query. So we should have 5 blue points where the distances are drawn from these blue match distributions, and also have 5 red data points. So because the two distance distributions have overlappings, the data points from these two distributions may also have overlaps. So it is impossible to perfectly set a threshold that can achieve 100% accuracy. So how should we set the distance threshold then? Intuitively, it's a good threshold. It's a good strategy to set the thresholds to be somewhere in the middle. So if we set the distance threshold to be at the middle intersection of these two PDFs, then we would have 8 out of 10 data points correctly classified. So the correctly classified data points are circled in orange, and then the total accuracy is 80%. And because there are 4 out of 5 blue points that are correctly classified, and also 4 out of 5 red points that are correctly classified, the false positive rate and false negative rate are both 20%. And what if we move the threshold a bit to the right? Well, you would decrease the false negative rate to 0 because now the other blue points is also correctly classified. However, the false positive rate increases to 60%, and the total accuracy drops to 70%. So you can see that setting a threshold is a trade-off between the false positive rate and false negative rate. Okay, let me now formally introduce the accuracy analysis for the threshold-based queries. As a reminder, the last two parameters for the threshold-based queries are the required or the maximum false positive and false negative rates user provided. So these two numbers, these two upper bounds, first limit the threshold to a certain range. And here we apply CDF or PDF to the distributions to get their cumulative distribution function or probability density function. Now we have a range for the threshold, and in this range, we would try to maximize the given accuracy with the given ratio of matches and not matches. So here, this expression is for when the ratio of matches and not match is 1-to-1. However, we also support the general case where they may have imbalanced data. And if we take the derivative of the accuracy to the threshold, and we can find that the optimal threshold is the point in this range we derived that's closest to the middle intersection of these two PDFs. So now we can set the optimal threshold, and with this optimal threshold, we can compute the accuracy we can achieve. And this accuracy is compared to the required accuracy in the specification. And then this result is returned to the optimization algorithm. Okay, this is for the threshold-based queries. Now let's dive into the winner-take-all-based queries. So again, I'll first introduce the intuitions and then the formal formulations. So this is an example of the winner-take-all query, where also the first three parameters are the query data structure expressions and the intersection size k we are testing for. And the fourth parameter here is W equals 5 matches. That means we have a total of 5 matches. And the fifth parameter is M equals 10 here, which means there are total M equals 10 data samples. So in summary, we have 5 matches and 10 minus W equals 5 not matches. And the sixth parameter is the specified accuracy for the standard winner-take-all inference. By standard winner-take-all inference, I mean that you just return the top W or the top 5 here. And it is called accurate if and only if the top 5 with the smallest distances are exactly the 5 matches. And the last two parameters specify a soft constraint, which is that if you want to return more than W equals 5 data samples with the smallest distances, you would hope that the top T equals 8 here contain all the matches. And we want this probability that the top T contain all the matches to be a high probability. And the last parameter here is the probabilities a lower bound. Okay, so now let's see how we perform in these winner-take-all based queries. We assume that we still have these 10 data points. And if we use the standard inference, that is, if we return the top 5, then we find that this result is not accurate because we did not successfully return all the matches. So this is an inaccurate result. But if you consider the soft constraint, or if you return the top T equals 8, you'll find that all the 5 matches are correctly returned. So this result conforms to the soft constraint. Okay, as you can see, unlike threshold-based queries, for winner-take-all based queries, HIME cannot set a threshold or tune anything. HIME would just calculate the accuracy, the probabilities that the accuracy constraints are satisfied, and then use this information to inform the optimization algorithm, whether the hypervector size should be larger or smaller. And here is the formal definitions for the winner-take-all queries. So first, we will calculate the accuracy of the standard inference. So as a reminder, the winner-take-all result is accurate if and only if the W matches have the smallest distances out of the total M data samples. And this part here is the probability that the maximum distance of the W matches is X. And the other part is the probability density that all the other non-matches have distances that's greater than or equal to X. And if we take the integral over all the X, we would get the expected accuracy. And for the soft accuracy constraint, we also calculate the probability that it is satisfied. And as a reminder, the soft accuracy constraint holds if and only if the distances of the W matches are all in the top T smallest. And here, the first part, this is the same as the standard accuracy. This part is the probability density that the maximum distance of the W matches is X. And all the other parts is the probability that there are I non-matches that have a distance that's less than X. and all the other non-matches have a distances at least x. And here we need to multiply this by a binomial coefficient because you need to choose I from the total m minus w negatives that have a small distance. Okay, so with these two formulas, we can calculate the expected accuracy and the probability that the soft accuracy constraint is satisfied. We then compare them to the specified lower bound and return it to the optimization algorithm. Okay, as you can see, in the accuracy analysis procedures, it is essential to know the analytical model or the distance distributions in advance. So how did we derive the distance distributions? Let me now introduce you the analytical model. As a reminder, the analytical model is provided with a hypervector size n, and then it derives the distance distributions for the match and the not match cases, which are phi m and phi nm. Well, I'll first introduce the basic formulations here. We call a code a randomly generated hypervector that maps to a distinct atomic symbols. So the codes, for example, here in the knowledge graph are act, place, and tennis. These are the interactions, the labels, and the concepts. And the tuple is the product or binding of one or more codes. So an edge in the knowledge graph, for example, is a tuple because it's a binding of several codes. And we call a set of codes or tuples is a sum or bundle of one or more codes or tuples. So in the knowledge graph example, each data structure hypervector for each node is a set of edges or of tuples. Okay, so the analytical model depends on the query and the data structure HD expressions and also the intersection size K. So we would compute the expected distances by analyzing the query and data structure expressions and the K, and we categorize them into three data structure, query data structure, or QDS predicates. And each QDS predicate is associated with the expected distances for the match and not match distributions, and also an independent constraint on the query and the data structures for the analysis to be valid. We will elaborate on this independence constraint later. So let me first introduce the first two type 1 and type 2 QDS predicates. For the first QDS predicates, the query is in the form of a tuple, and the data structure is a tuple set. And this essentially says we want to test, we want to do a single element tuple test, membership test on a tuple set. And the type 2 QDS predicates, the query and the data structures are both tuple sets, and we want to test whether their intersection size is at least k. And the expected distances for the match distribution for these two QDS types have been derived by prior work and is shown here. You might notice that here we also specifies the independence constraint that must be satisfied for these two QDS predicates. And for these two QDS predicates, the query and data structures must be independent tuple sets. And what does independent tuple set means? So independent set is a set of tuples, and we say that this set of tuples is an independent set if and only if no tuple can be represented by a binding of other tuples in the set. To help you understand, if we have an expression here that is a plus b times c at a plus b, then this is not an independent set, because if we flatten it to a set of tuples, then it will be AC, BC, and AB. And here AB is the binding of the other two tuples. This uses the property of BSC that the binding is self-inverse, and the C cancels out here. Okay, so this is not an independent set. And for all the independent sets, the QDS1 and QDS2 can work with. Okay, now let me introduce the type 3, the last type of the QDS predicates, where the the query is also a single element, a single tuple. However, the data structure is different from QDS1. Instead of a simple tuple set, in QDS3, the data structure is a binding of code or tuple sets. And here, the independence constraint is also different. Here we specify that the data structure must be an independent product, and we will introduce what independent product is in the next slide. So for this QDS predicate, we also derive the expected distances and for the match distribution, and it is as follows. And usually we would use only the special case where W equals 2. And this is used in the database analogy inference and also in the non-deterministic finite state automata transitions. Okay, now let me introduce you what is an independent product. Well, an independent product first is a binding of several tuple sets or code sets. And we define this as an independent product if and only if the union of all the sets bound together is an independent set. As an example, this A plus B binds C plus D is not an independent is an independent tuple, is an independent product because the union of these two sets are A plus B, A, B, C, D, which are four independent codes. And a counterexample is AB plus AC binds BC plus BD because the union of these two sets are AB, AC, BC, BD. And we just show that AB can be represented by the binding of AC and BC. So the union is not an independent set, which means the binding of these two sets is not an independent product. And it should be noted that independent products are usually not independent sets after they flatten, because you can flatten them to also be in the form of a set of tuples. However, usually they are not independent set. So that's why we need another independent constraint and also another QDS predicate to formalize them. Okay, so now that we have the expected distances for the different cases, but we haven't taken the hardware errors into account. Now we want to adjust the expected distances based on the hardware errors. And how do we do that? We start with the expected distances that we currently have, and also the hardware error model we work with. Now we first compute a bit error rate upper bound that any bit flip happens in the hardware. And then we use this upper bound bit flip rate to adjust the expected distances. And it should be noted that this using upper bound of the bit error rate is sound because the higher bit error rate you have, the less accurate you would get. Okay, now that we have the adjusted expected distances, we can then derive the variance and the final analytical model. So first, because we work with the BSC binary hypervectors, and here X is the difference between two elements in the binary hypervectors. So X is also a binary random variable. And that's why the second moment of X is the same as the expected distance of X, the expected value of X. And so we can calculate the variance from the adjusted expected values. And then we model the distributions as a normal distribution with the expected value and the standard deviation. And here the normal approximation is justified by the central limit theorem, as the Hamming distance is essentially an average over many IID random variables. And also this is a standard practice used by prior theoretical work. Okay, since independence constraints play a big role in our analytical model, we'll talk more about it in the next few slides. So first, we help the users to check whether they provide an independent HG expression. We derive an efficient mutual independence checker. But this checker is optional and can be disabled at runtime so that it does not induce any overhead in the runtime. And one may also notice that the independence constraints are somewhat similar to the statistical independence. And actually, one can prove that the independent set constraint is equivalent to that the tuple hypervector values are statistically mutually independent. And one may also wonder whether these independence constraints limit our expressivity. But actually, a wide range of data structures can be represented by mutually independent sets or product. In our work, we derive set, knowledge graph, databases, and NFA. But there are other data structures that can be also represented by mutually independent sets or product. However, if certain applications explicitly use correlated data structures, then you cannot analyze it with HAIM. For example, the language classifications use trigrams, and some trigrams are correlated to each other. And we also note that a precise analysis of distance distributions of correlated data structures is hard because there are extreme cases. For example, here, although the tuple AB is a member of the tuple set G here, but since G is not an independent set, and we found that the expected distance between AB and G is actually 0.5, which is the same as the expected distance between two random independent hypervectors. So that makes AB completely indistinguishable from another independent hypervector for G. Okay, finally, let's go to talk about the HAIM's optimization framework, the top level. So HAIM's optimization algorithm searches the binary hypervector size n, and then provide n to the other two components. Then it is informed whether the size n should be larger or can be smaller. So intuitively, the top-level optimization framework just do a binary search over the hypervector sizes, and then uses the accuracy analysis to decide where to go in the next binary search. And it stores the parameters for each query so that we can use them for query-specific optimizations at runtime. And finally, the global optimal hypervector size is set to be the maximum of all the optimal sizes for all the queries. Okay, now let's look at how HAIM perform. Let's look at the evaluation results. So to evaluate HAIM, we create 5 HGC-based data structures, and 4 of them use threshold-based queries, and 1 of them uses winner-take-all-based queries. For each benchmark, we parameterize them with 5 different sizes. And we compare HAIM against both the static optimization, which we call DT-par, and the dynamic tuning, which we call DT-all baselines. And we configure all the methods to try to deliver a 99% query accuracy. We'll first look at the runtime. So we can see that HAIM runs in milliseconds, and also it is orders of magnitude faster than dynamically tuning-based approaches. And it should be also noted that HAIM's analysis, because HAIM's analysis is analytical, the runtime the trend is quite flat. It means that HAIM does not depend on the data structure size. However, for DT-par or DT-all, they should do Monte Carlo simulations and generate random data structures to tune. So their runtime increase with the increase of data structure sizes. And now let's look at the accuracy. So for each parameterized benchmark, we sample 100 data structures that conforms to the specification. And we test the parameterization on each random data structure with random queries and random codeblocks. And here each line draws the median accuracy with arrow bars representing the quartiles. We can find that HAIM-derived parameters consistently meet the accuracy target. And also, for certain benchmarks, the difference is quite significant. HAIM is able to find parameterizations that dynamically tuning simply cannot find. And we also did an ablation study, since HAIM sometimes use different hypervector sizes than dynamically tuned. So we control that we create another baseline called DT hybrid that uses dynamically tuning's hypervector size and use HIME to derive the thresholds. And we find that DT hybrid consistently outperforms DTO. And that means HIME-derived thresholds are optimal and better than dynamically tuned. And for hypervector sizes, we find that for the parameterizations where the baselines achieve similar accuracies, HIME identifies a 1.15 smaller hypervector sizes than the dynamically tuning-based approaches. Okay, and since HIME is hardware aware, we also try to use HIME on the emerging hardware technologies. For the first set of experiments, we target an emerging hardware technology called resistive RAM, where you can store more than 1 bit on one memory cell. But with the higher information density, you would also get higher bit error rate. With HIME, we can perform an ISO accuracy analysis because HIME can automatically adjust the hypervector sizes based on the bit error rate. And we find that in this case study, the 2 bit per cell bit error, 2 bit per cell RRAM outperforms the 3 bit per cell RRAM and also the error-free hardware. Although the 3 bit per cell bit error rate RRAM has a higher memory density, it has much higher bit error rate, so that HIME needs to provide it with much larger dimensionality, which cancels out the benefit. So this is exciting because this shows that HIME enables a systematic applications to devices analysis. And we also use HIME to find that with analog content addressable memory to speed up the item memory lookup, we can also speed up the HDC inference procedure. In conclusion, we presented HIME, the first static analysis framework for HDC that minimizes the resource usage in the presence of hardware error. And HIME achieves better accuracy than dynamically tuning with a guarantee, and is also orders of magnitude faster. We also show that HIME enables an ISO accuracy systematic application to device analysis. In the future, we envision HIME as a sound core and the basis for future analysis that may be unsung, but can apply to more practical applications. Thank you.
Luke, thank you very much for this exciting talk. Thank you. So I see immediately there was a question in the chat by Joshua Cinnamon. Maybe Joshua, you can unmute yourself and
sure.
Yes.
So I was curious when you talked about independence sort of as an analog of like linear dependence in a vector space. Aren't there situations where you'd have a collection of vectors where one of them you have like a sort of pseudo independence, that there's a linear combination of the others that's close, that's related to it, that's some certain amount similar but not the same? So doesn't that end up being a probabilistic concept, not a binary decision? I don't know, I guess subject to the threshold, it becomes binary.
Well, I think because we target in this work we target like atomic hypervectors that that represent discrete symbols. So here the independence is on whether like the HT expressions, not the actual like hypervector values, right? So I think this is a deterministic whether the tuples are or the set is independent or not, because you can just look at the tuple expressions to see whether they are independent or not. It's not like the hypervectors are independent in the hyperdimensional space, but rather independence of the tuple or HD expressions. Yeah, does that make sense?
It does. I still wonder if you had a very large set, if it would look like it was like you had dependencies, but they were functionally independent or the other way around, but maybe I'm just mixed up about it.
Yeah, I guess like because here there are essentially two spaces. The first space is like the space of the variables or the atomic symbols, and the second space is like the hypervector, the hyperdimensional space that where the hypervectors live. So here the independence constraint is on the variable space kind of. So provided with the symbols, you can deterministically check whether they are independent or not.
Okay. Thank you.
More questions to Luke?
Yeah, I have one.
Yeah, go on.
Thank you. Are you working also with Philip Wong?
No, I'm not
Stanford?
working with Philip Wong.
Okay,
We do
thank
meet with one of his students, but we don't work directly with him. We've worked on some of the memory technologies that have come out of his group, though, or worked with indirectly with some of the memory technologies. So it's not like a direct collaboration, but there's some overlap.
Yeah, that's what I was thinking. So are you actually going to be performing analysis on real silicon?
So the RM numbers are actually numbers that we collected from real silicon, and we actually have a companion paper not related to HDC that involves characterizing this hardware. And part of that characterization involves characterizing the bit error rates. So that's from silicon. The CAM error rates are from paper where someone fabricated out like a CAM for HDC.
What's the date of publication?
For the CAM for the HDC CAM?
For the paper, yeah.
For which hardware technology?
Resistive.
The resistive. We just got it accepted to ICCAD, so it's also 2023.
Okay, thank you.
Mm-hmm.
Some more questions? Well, let's see.
Well, I have a add-on to it.
Yeah, sure.
The idea of having resistive memory, it's because it's extremely cheap to produce and it has good geometry decline rates. And basically it can be printed very easily for high volume production. Is there any crossover there that you see at this time?
So you're asking about whether there is a nice match between HDC and resistive RAM as a memory technology?
Yes. Yes.
Yeah, I mean, I think, yeah, I mean, it's it's an attractive form of non-volatile storage. Like that's like one of the things that's attractive, right? So you can store things like your basis hypervectors, for example, in resistive RAM, and then if there's bit corruptions that occur, you can potentially still live, with those bit corruptions while still getting some sort of accuracy guarantee. And then the other thing too is a lot of these resistive memory technologies, right? You can use them in things like content addressable memories. And typically with those sorts of memories, you need a resistive memory, right? Because otherwise you can't do the computation in memories as easily. Did I answer your question?
Yes, it did. Are you doing any in self-organizing memory?
Self-organizing memory. I'm actually not familiar with that. What is it?
That's good. Thank you.
No, I just I'm curious. Like, can I get a definition at least?
It's a memory that takes streaming input and organizes it amongst the major areas of similarities.
Interesting. Okay. Yeah, I mean, we've been thinking about hyperdimensional computing as a streaming type, computational model, right? Because all of your operations are per bit, at least in this with BSC. And so there is
more. Go ahead.
Yeah, and I was just saying that because all your operations are per bit, there's a lot you can do where you can kind of turn into a reduction that you kind of compute incrementally, right? And that leads to some interesting optimizations that can be done. But maybe you mean that you have a different definition of streaming. I don't know.
Yeah, we call the structure a canopy. The idea here is that it's pretty is to take and allow that stream to be high rate matched by the gross memory, if you will, the larger memory. And to do that requires the networking to be carried out in a highly parallel nature. And it requires, almost speaks to very slow memory, which says that you can use resistive. It's very ideal for resistive memory. There's a nice, yeah, it's a nice spline. All right, that's. I better shut up.
Yeah, thanks for the overview.
Ross, I see your microphone is on. Did you have a question?
I do indeed. Thank you very much, Luke, for that talk. Very interesting. You're finding that dynamic tuning doesn't generalize very well, or certainly not as well as HIME, is, I think, very interesting and very important for the field as a whole, because it's such a common procedure for everybody to use in their research. So I'd be very interested to know if you've got any thoughts on the mechanical reasons why dynamic tuning doesn't appear to generalize as well as is obviously possible via HIME.
Yeah. So, yeah. First reason is that like that for dynamic tuning, you have a limited time and you can only do a limited like samples of, for example, code books, hardware errors, and also the data structures that conform to some certain specifications. And also, because you have limited time, you can only, for example, search limited like parameter space. So, like for threshold-based queries, you may not be able to like search multiple threshold at a finer granularity because there is time constraint. But for HIME, because it's analytical and computes very fast, it can compute the multiple threshold, and that also increases its like generality.
Okay, so I mean, your argument then is that the with DT, essentially it's a single sample from a distribution, whereas with HIME, you're assessing the entire distribution.
Well, I would say it's not necessarily a single sample, but like it's a trade-off between like how much you sample and like the time you spend. So like to get a very generalized result or to get very good accuracy constraint, you need many samples and much optimization time. So it's a trade-off. But for HIME, like because it's analytical, so you can get the guarantee and generalization for free, kind of. That's my understanding.
Okay, thanks very much for that. Thank you.
Thank you for the question.
Look, I have very practical question. What about availability of HIME software? I mean, for public usage.
Yeah. So I guess
it's open source. Yeah, and I guess I will also add in our community. In our community, it's actually standard practice that you submit a reproducible software package. So it's also been audited by, you know, another group of people. That.
So is it part? So the link, is it part of the paper? I mean,
yeah. So when the paper is, I guess when OOPSLA decides to release the paper, it'll have a stamp, and then that will also be attached to a DOI link for the software package. And we also have a GitHub repo, but the GitHub repo is likely to drift, right, as we keep working on it.
Yeah.
But software package is that to be a snapshot. So.
But if I may ask you, I mean, whenever it is available in more or less clean form, please communicate the link to me so I can post it on the website. I mean, along with your with the information about your talk. I think it should be of practical interest for many people in the community in this kind of optimization-based parameter choosing.
Yeah, no, we'd be happy to. And if you, you know, if there's any theoretical results you think could be useful for us to incorporate into our analysis or to turn into an analysis, you can also reach out to us, and yeah, we're happy to work together.
All right, let me do some last check about possible questions in the audience. Well, if not, then I would like to thank you, Luke, and you, Sarah, once again for coming over and giving this great talk. So see you next time. And yes, stay tuned. So we see you in 2 weeks from now on VSAONLINE. Thank you and goodbye.
Yeah. Thanks for having us.
Bye.
Bye-bye.